So we're moving into our exponential and logistic unit. We're going to take a look at these two types of functions today, see what each of them are, what they're represented by, all that good stuff. So just to start us off, we have two functions. F of x is x squared and g of x is 2 to the x. Very similar, however, slightly different. If we look at f of x, we can see the base is a variable, okay? And the exponent is going to be a constant. So if I'm looking at a variable for a base, that is considered to be a power function. Okay, versus g of x, where the base is now a constant, and your exponent is your variable. So once you see your exponent as your variable, that's where we get this exponential function. So when we're talking exponential functions, you always want to think base is a number, a constant, and then the exponent is a variable. Okay, so I'm taking a look. It says we're going to state whether the following functions are exponential functions. So again, looking for base is a constant, exponent as a variable. Then what we're going to do is find what the initial value would be, and your initial value is always going to be when x is equal to 0. And the base is going to be what your exponent is raised to. So for this first one, for letter A, if I'm looking at 3 to the x, so my base is a constant, my exponent is a variable, so I can say yes, this is an exponential function. And we just said your base was going to be 3, that's your constant. Now your initial value is when you make x 0. So if I take 3 and I raise it to the 0 power, anything raised to the 0 power is 1. So your initial value is 1. You can also think of that as your y-intercept. So for your exponential function, not only did you find the initial value, but you also have the y-intercept at 0, 1. Okay. Letter B, if we're looking at this, now I see here I have an exponent that is a number versus a variable. I also see a base being a variable rather than a constant. So for this one, I would have to say, no, this is a power function, not an exponential function. And again, we said the base is a variable, and your exponent is a constant. So those two are opposites. Okay, if we're looking at letter C. So letter C, this is, yes, an exponential function. So if I'm trying to determine the base of this function, the base, now this is a little different because we had a number in front. The base is always what the exponent is raised to, and only the number that the exponent is raised to. So we can say here, the base is 1.5. To find that initial value, again, keep in mind what you're doing is you're making x 0. So you have 2 times 1.5 raised to the 0. Be careful with orders of operations. 1.5 to the 0 goes first, so anything to the 0 power is 1. 2 times 1 will be 2. So your initial value on this is now 2. Ooh, and it should be a negative. I lost that negative there. So sorry, we should have a negative in front. So how about your initial value is a negative 2? Okay. And if we're looking at letter D, again, I have, it looks like an exponent that is a variable. So yes, this again is an exponential function. We can say here, now your base we have to be careful with. Your base we have to go back and think some exponential rules. If I just look at the base on the side, I could rewrite this base as being 2 to the negative 1 to the x, because if I think power to a power, I multiply. Negative 1 times x would give me negative x, so those two things are the same exact expression. Now I want to think, well, what does a negative exponent do? So a negative exponent, I always think, does the reciprocal of what the number actually is. So the reciprocal of 2 is 1/2. And now your exponent is positive, so it's 1/2 to the positive 1 raised to the x. Okay, so now if we go back and ask or answer the question, what's your base? The base going to be 1/2. If we're trying to find your initial value, okay, so your initial value is still plugging in 0. So if I go and I rewrite this function, this is 7 times 1/2 to the 0. So anything to the 0 is 1. 7 times 1 is going to get you 7. Okay, so for number 2, we're going to take a look, and it says without a calculator, we're going to try and compute the exponential function values. Okay, and we're using, again, this function 2 to the x. So again, it's an exponential function. Your exponent is a variable. So if we were to plug in 4, this is saying 2 to the 4th power. Keep in mind what that's saying. It's saying 2 times 2 times 2 times 2. So if we did 2 to the 4th power, or 2 4 times, we're going to get a value of 16. Okay. For letter B, we have 2 to the 0 power, and like we set up above, 2 to the 0, anything to the 0, is going to get you a value of 1. On the bottom here, we have f of -3. So if I'm thinking f of -3, now again, we have that negative exponent. So this is like saying 2 to the -3 power. So we could really rewrite this as 2 to the -1 raised to the 3. Those two things are equivalent expressions. And again, if we have that negative exponent, I want to think, let's make it positive. So if we make it positive, we think take the reciprocal of the number. So this is what we're really dealing with. So we have 1/2 to the 3rd power. So again, it's like saying 1/2 times 1/2 times 1/2. And when you multiply fractions, I always think tops with tops, bottoms with bottoms. That would get us a value of 1/8. Okay, f of 1/2. So this is now saying 2 to the 1/2 power. So fractional exponents really would turn into roots. And if I turn this into a root, I always think my denominator goes on the outside of the root, where the numerator goes on the inside. So really what we have here, 2 to the 1/2, is really going to just be the square root of 2. Since we're doing it without a calculator, I'm not expecting you to know that decimal equivalent. Okay, and so now, last one, we have 2 raised to the -3/2. So we can do this a whole bunch of different ways here. I'm going to start by saying, let's rewrite this kind of like we did with our other negative exponents. I'm going to say this is like 2 to the -1 raised to the 3/2. So that -1, we said would turn it into a fraction, so that's going to get me 1/2. Now our 3/2 is going to act like a root. So again, the bottom number goes on the outside. That's telling me the root I have. So I have the square root of 1/2 to the 3rd power. Okay. So if I take 1/2 and I cube it, well, we did that already, and we know that that's going to be 1/8. And now properties of roots, I can square root the top and square root the bottom. And this will simplify down then. The square root of 1 is 1 over the square root of 8. And it's not rationalized, but that's okay. Okay, so on the back, we're going to take a look at, so what if I just have values? How am I going to be able to figure out some exponential functions from here? Well, when we took a look at our functions on the front, we said anything when x was 0, that was always going to give us our initial value. So sometimes I like to start there, and I like to try and figure out how would I have changed. Sometimes when you have fractions, maybe that's a little bit difficult. For f of x, that maybe is a little bit difficult. So maybe let's start back here on this value. When x is -2, we have a 6. When x is -1, I have a 3. So I want to think, well, what happened here? Well, if I multiplied 6 by 1/2, I would get 3. So then that same question, well, could I do that again? 3 times 1/2 gets me 3/2. And if I try that again, 3/2 times 1/2 gets me 3/4, and the same thing to 3/8. So what is that telling me? Well, that's telling me I found my initial value. Like we said, my initial value is 3/2. What we've also found here is our base being 1/2, and I can raise that to the x. Okay, so if we even check that out, if I plugged in 0 for x, anything to the 0 power we know is 1, and 1 times 3/2 gives us that initial value of 3/2 back. Okay. Same thing over here. When we're starting, again, our initial value we know is 12, so that's kind of nice. I can start it off there. Now we're just trying to look for that base. So again, if I go from 12 to 4, well, I'm really multiplying it by 1/3. And double check. If I go from 4 to 4/3, again, multiplying that by 1/3. So that's showing me my base. That's 1/3. Raise it to the x, and I'm going to get my exponential function. Okay. So things to be aware of. When you have exponential functions, we can either have growths or we can have decays. So if we're looking at this notation, thinking of this as our formula, it says, so if a is greater than 0 and b is greater than 1, the function is increasing and is an exponential growth. The base b is going to be considered its growth factor. So I can either call it the base or I can call it the growth factor. Now, if a is greater than 0 and b is less than 1, so think fractional value, so 1/2, 1/3, like the numbers that we saw up above, this would be decreasing and is an exponential decay. And the base b, since it's decaying, is its decay factor. In other words, how it's getting smaller. Okay, so if that number, that b value is greater than 1, it's growth. If it's fractional value, think between 0 and 1, then it would be a decay, and it would be getting smaller. Okay, so some examples here. This g of x function, it's a growth function because I can see the base is 5, 5 being greater than 1. It's going to grow by a factor of 5. That's its growth factor. If I take a look at h of x, now again I can see its base is 1/3. Since that's less than 1, in between 0 and 1, it's an exponential decay. And so I can see every time x increases by 1, it's going to decrease by a factor of 1/3. Okay, so we can see, let's try a couple of these. So we're going to take a look now and think of this as transformations. Okay, so again, we're using this basic function 2 to the x, and I just want to think of this in terms of transformations. So looking at our g of x function, I can see I have x minus 1. So anytime I'm changing the x value, I always want to think those are like kind of opposite motions. So if I'm subtracting 1 from the x, that maybe would make me think go to the left, but really opposite, we're going to the right by a value of 1. Okay. For letter B, I've now negated the x. So anytime I negate the x, I want to think that's a reflection. If I negate the x, I'm reflecting over the y-axis. And for letter C, we're multiplying the entire function by 3. So anytime I multiply an entire function by a number, it's got to be a vertical change, and since this is a whole value, this is a vertical stretch. We always said vertical motions, up, down, or stretches would be normal. Horizontal motions, left, right, or stretches, shrinks would be opposite of what we'd think. Okay. And then our last thing that we're going to take a look at is our logistic growth functions. This is one of our 12 basic functions. This is the one we said kind of looked like a zombie graph. So we have A, B, C, K. They're all positive constraints, with B being less than 1, so think fractional value. Okay. It says a logistic growth function in X is a function that can be written in this form. So notice we have a couple of different forms. We have B raised to the X, or we have E raised to the X. Those are both exponential functions. Again, they're both bases are constants and the exponents are variables. And it says where the constant C, that numerator value, is what's called your limit to growth. In other words, think horizontal asymptotes. Okay. If that B value was greater than 1, or K would be less than 0, then what we would get is something called a logistic decay function. Most of the time we're going to be dealing with growth functions, but if you were to see one of those values pop up, or you could see it sloping down to the right, then you would know it's a decay function. Here, this is our basic logistic function. Okay, and if you notice, growth factor, we talked about that limit to growth. This here would be like y equals c. But what you're also going to notice is that you also have another horizontal asymptote, and that horizontal asymptote is always at 0. So unless it's been shifted up or down, you will get two asymptotes, one at 0 and one at your growth, limit to growth. So if we're looking at A and B, we have to find both the y-intercept and the horizontal asymptotes. So y-intercept, you make x 0. So if we look at this function, this may look crazy. It's going to be much easier to solve when you just kind of think about it. Anything to the 0 power is 1. 3 times 1 is 3 plus 1 is 4. So that gets me something that looks like 8 over 4, and we know 8 over 4 is 2. So I can say your y-intercept is 2, located at that coordinate. As far as your horizontal asymptotes, so the horizontal asymptotes, we said we would have 2 of them. It would always be your limit to growth, and in this case, your limit to growth is 8, and we also have that y equals 0. Okay, try one more. So if we're looking again for your y-intercept, we're going to make x 0. So on the bottom, now we have an e, but it works the same way. Okay, so start off with your exponents. Negative 3 times 0 is 0. Anything raised to the 0 is still 1, so e to the 0 is 1. Times 2 is 2, plus 1 is 3. So your denominator right now is 3. So we can say your y-intercept is at the location 0, 20 over 3. Your horizontal asymptotes, we can say again, we have 2 of them. It's always going to be that limit to growth, that numerator value, and y equals 0. Hope this helped. We'll do some more in class. Have a great day.